Imagine we're writing an employee management tool. For our core domain types, we start with an interface employee, and for now, salaried and freelancer are all the implementations we need. The next step is to add operations, to request and confirm signage of legal documents, to manage access to various platforms, to track completion of compliance trainings. Can you tell I'm working for a large corporation? To issue payments, to plan project work, to schedule holidays, etc. We quickly realized that it's probably a bad idea to place all those very disparate operations that interact with mostly separate subsystems on the same type. Imagine employee gobbling up all that functionality and in turn, depending on most of our system. I shudder at the thought. So we need to separate the operations from the type. We leaf through our copy of design patterns and land on the visitor pattern. Immediately, the shudder returns and we wonder, isn't there a simpler way? And the answer is, in Java 21, there absolutely is. Just like lambda expressions turned the strategy pattern into language features so we hardly think of it as a design pattern anymore, does pattern matching turn the separation of types and operations into a simple application of a few language features, namely patterns, switch, and sealed types. And that's what this last episode on the road to Java 21 is all about. So let's get started. So it should come as no surprise that this is what's called pattern matching.
Pattern matching lets you construct your own data-driven dispatch in your implementation code rather than an API code.
We'll take things slowly and start with a feature that you, if you're on Java 17, might already have used, the extended instance of. The old clunky way to type check with instance of consists of 3 steps. The type check, the declaration of a new variable, and a cast of the general variable into the new one. The extended instance of combines all 3 steps into just one operation. With a simple if employee instance of freelancer, we get the type check, a new variable of the desired type and name, and the old variable cast into it. We can use the new variable freelancer everywhere where the condition is true, in this case in the if branch. Now, if we want to implement an operation that accepts an employee instance but needs to handle each type differently, we could create a series of instance of checks that runs through all known subtypes. I know you're feeling that shudder again, but stick with me, it's only a hypothetical step on the path to a good solution. Let's analyze it though. If the method doesn't return anything, the if-else-if chain doesn't need to cover all cases. And if we add an additional class, contractor implements employee for example, we suddenly get no behavior at all for its instances, and that's not good. So it's probably a good idea to at least add an else branch that throws an exception, but then we still only find out at runtime that a branch is missing. That's a serious maintainability problem and the reason for the shudder you felt earlier when I started going down this road. We need to improve over this. But let's put a pin in it for now and turn to another feature that's already available in 17, one you've probably used way more often. The good old switch statement has seen 2 important improvements. One is that we can use it as an expression, meaning it computes a value that we, for example, assign to a variable on the left-hand side or return from a method. Where to use this depends on context. Do we need to compute a value? Then we'll use switch as an expression. Or do we just execute some code? Then a statement is fine. The other improvement is that instead of following up the case label with a colon, we can now use the lambda arrow, which eliminates fall through and thus the need for all those breaks. This should definitely be your default choice, unless you intentionally want to fall through. Now, imagine for a moment that instead of an employee interface with 2 implementations, we had created an employee type enum with 2 values, salaried and freelancer. Then one way to implement an operation that differentiates by type would be to switch over employee.type and to write a case for each enum value. We can use the fancy new array syntax, but there doesn't seem to be a need for a switch expression, and so it's a statement. Unfortunately, a switch over enum statement doesn't need to cover all cases either, and so we get the same behavior as with the if-else-if chain, where a new enum value is silently ignored. We can add a default branch that at least throws an exception, but we would still rely on tests to find errors before they occur in production. Still the same maintainability problem, still needs improvement. On the way there, let's combine the 2 approaches. We're back to an interface with 2 implementations, but now we're using the type check from the extended instance of in switch. This is only possible without additional command line flags since Java 21. As you can probably tell by now, a line like case freelancer arrow something checks whether employee is an instance of freelancer, and if so, executes the code on the right where a variable of name freelancer and of type freelancer is available. At first, the only advantage of this is that we have the expressiveness of the switch that clearly communicates that we have one action per branch, while not needing an additional enum to differentiate by type. The class information suffices. The game changer is hidden in between the last case and the end of the switch. See what happens when I remove the default branch. We get a compile error. That's because the compiler requires that a switch over a complex type covers all possible implementations. As is, that only forces us to include a default branch, but now we'll fold in another Java feature that you might already be using on JDK 17, although that would surprise me a bit because it didn't really get you anything. And that's sealed types. Regular types can be implemented by anybody who can get a hold of them and, in the case of a class, can reach the superconstructor. For simplicity's sake, let's stick to interfaces though. The only way to limit an interface's extensibility is via its visibility. Otherwise, everybody can implement it. And that's fine for things like collection or list, but with core domain types that have a lot of logic attached to them, it's not really feasible to expect that simply adding an implementation like a contractor for employee just works and doesn't require any other changes in the system. No, your code probably depends on you knowing every implementation of that interface. And that's what sealed interfaces are for. You can declare an interface like employee sealed and then permit all possible implementations. In our case, that's salaried and freelancer. There are some requirements for the types that implement a sealed interface or extend a sealed class, but I gloss over that here. There's a link to a detailed explanation of sealed types in the description. What's important for us here, and really 80% of what sealed types are about, is that the compiler understands the limited extensibility. For a sealed interface, employee permits salaried and freelancer. It knows that when you have an instance of employee, it must be either an instance of salaried or of freelancer. And with this final ingredient, we get our compile time verification of operations that need to differentiate by type. Because look what happens to our switch when we make employee sealed. The compile error is gone. The compiler understands that we covered all possible subtypes of employee. That's called exhaustiveness or being exhaustive, and it stops bothering us. But at the same time, it's still watching us closely. Because when we add a third implementation, we also need to add it to the permits clause, and bam! The compile error is back. This is huge. This is what the entire complexity of the visitor pattern was there for, to separate types from operations while making sure that adding a new type forces us to update all operations to handle it. This way, we get the same safety. All we have to do is make the type sealed. And avoid default branches. That's important. Let's talk about that for a minute. When switching over complex types, the compiler requires exhaustiveness. The trivial way to achieve that is to add a default branch, but the critical disadvantage of that is that if we add another implementation of the sealed type, the switch is still exhaustive and we don't get a compile error, and so we don't have to update our operation for the new type and it silently falls into the default branch. That may be the correct way to handle it, but it also might not be, and it's really only the developer, us, who can make that decision. So it's important to avoid an outright default branch and instead list all types explicitly. We cannot combine multiple types into one branch, and so in the worst case, we may have to repeat the same behavior for a few different types. If only there was a better way to handle this. And that, my friends, is called foreshadowing. I'm alluding to something that happens later in the video to build anticipation and add tension, so you stick around for the important things that are coming instead of switching to cat videos. Are those still a thing? Or am I dating myself? Anyway, before we resolve this tension, let's talk about the term in the title of this video that I didn't even explain yet. Pattern matching. Remember the instance of triad? A check, a declaration, a cast? If we generalize this to a check, declarations, extractions, we get something much more powerful. For example, if the employee is of type freelancer, declare variable freelancer free and assign the employee to it. Or, if the freelancer is composed of a name and an hourly rate larger than 250 euros, create a variable string name and assign the freelancer's name to it because we probably want to fire them. Or, if the list of string is not empty, declare variables string first and list of string tail and assign the first element of the list to first and the rest of the list to tail. Or, If the map from ID to user contains an entry for specific ID, declare a variable user_u and assign the user associated with that variable. Checking a variable for some property and then declaring new variables to capture that property is extremely common. What you're doing here is matching a variable to a pattern, and if it fits, extracting information according to that pattern. So it should come as no surprise that this is what's called pattern matching. The extended instance of and its counterpart in switches are called type patterns, but that's not the only pattern Java has on offer. But before we get to the other one, let's zoom out a bit. There's a bigger picture of what pattern matching means for Java. And who better to explain it than Java language architect and player of long games, Brian Getz.
So pattern matching is related to dynamic dispatch. And historically, Java's approach to dynamic dispatch is tied strictly to the class hierarchy. So we define a virtual method through an interface or a base class, and then subclasses provide their own implementations, and the method invocation mechanics handles the dynamic dispatch. And this is really powerful, but it's rigid, because in order to harness the power of this dynamic dispatch, we have to reflect the dispatch points as public API points and reflect each dispatch option as a separate implementation of the type declaring the dispatch point. This works great when the dynamic behavior is something that we really want as a first-class public API point. But sometimes we want to make dynamic, data-driven decisions without having to expose all of this on our APIs. So historically, the way we had to do this was with the visitor pattern. And this works, but it really just moves the problem somewhere else. So visitor lets you take polymorphic operations out of the public API for your domain model, but the flip side is that visitors are pretty intrusive and rigid in their own way. So pattern matching lets you construct your own data-driven dispatch in your implementation code rather than an API code. And this is more flexible, more concise, less intrusive, and can be used to yield benefits in several different ways. Now, pattern matching wouldn't and shouldn't replace API-based polymorphism. It complements it. Some polymorphic operations are essential to the domain, and they make total sense to be part of your API, and we'll continue to use public API points for these. Others don't really make sense to be part of your domain model, and pattern matching lets us more easily move these to where we belong. So pattern matching gives API designers a richer toolbox for exposing the right shape API. Now, if we were to decide that a particular polymorphic operation belongs in the API, pattern matching still offers us some extra flexibility. You can continue to use method overriding to implement the operation, but if you know all your subtypes, which is going to happen more frequently now that we have the ability to declare sealed class hierarchies, you can also write a single data-driven implementation using pattern matching. The clients won't be able to tell the difference, so if you have pattern matching in the language, even if you're not going to use it to change the structure of your APIs, it still offers implementation flexibility for API developers. And finally, pattern matching gives more flexibility to API clients because they can more easily and safely create new polymorphic behavior, even if the underlying domain model hasn't exposed it directly. So we should think of pattern matching as offering us another path to polymorphic dispatch that can be used in different situations from ordinary virtual dispatch. And if the data-oriented polymorphism of pattern matching is a better fit for your problem, you can use that, and otherwise we can continue to use the tried and true object-oriented techniques.
As Brian just explained, pattern matching can be used to implement polymorphism. In an object-oriented approach, that can occasionally complement polymorphism by inheritance. But we can take it much further and forgo OOP for most of our domain and pick a much more functional approach. But where functional programming places functions at the center, with data representation a close second, what I'm talking about switches that around, no pun intended, and focuses on data first. It's called data-oriented programming. Data-oriented programming proposes the representation of outside data in your program, not as objects that combine mutable state and operations and that data needs to be contorted to align with, but instead represented as closely as possible with simple, immutable types. We'll see in a second how to do that. You'd apply data-oriented programming in situations where a system or subsystem is mostly focused on ferrying data back and forth between a few connectors to outside systems. And that doesn't require the kind of modularization object-oriented design affords us. That is more likely if the system or subsystem is somewhat small. But how do you represent data as closely as possible? We'll see. The ingredients are relatively simple. The main one, and if you're on JDK 17, I'm sure you've already used it, are records. Designed as transparent carriers of immutable data, they're perfect for this task, and that's no coincidence, by the way. You'll use them to create types that represent specific data as closely as possible, so you get the most out of Java's type system. So if your data contains salaried employees with a name and a pay grade, as well as freelancers with a name and an hourly rate, don't try to find a smart way to combine that in one class. Just create two records that fit the data exactly and put in the work to make them airtight. You want to enforce all requirements for the data in the constructor or factor method to make sure that only legal states are represented. And by default, these types should be deeply mutable. Record fields cannot be reassigned, but if they reference a mutable type, say an array list, the collection could still be changed by calling add or clear. You probably want to assign a list.copyOff to the field instead. Still, some data might have non-required fields. We can argue whether to model them with null or give their components an optional type. I'm clearly in the latter camp, by the way. But don't let this seduce you into modeling an A or B scenario as a single type with tons of non-required fields. Instead, add the other ingredient, sealed types. You'll use them whenever there are alternatives between different kinds of data. So if your data contains contracts and each contract links to an employee that is either salaried or freelancer, you'd create a sealed interface employee that permits two implementations, salaried and freelancer. That nails our types down. Now let's talk about operations. Unless they just combine data on the same type, like a first name and a last name to a full name, they should not be defined on these types. Beyond that, you already know most of what you need to know about operations over these types from the first part of the video. But since we're now dealing with records a lot, let's add the other kind of pattern that I alluded to earlier. That would be record patterns. Remember this example? If the freelancer is composed of a name and an hourly rate larger than 250 euros, create a variable string name and assign the freelancer's name to it. That's exactly what record patterns do. The check is whether we indeed have an instance of the record, the declarations are one per component, and the extractions are assigning the component values to these variables. With record patterns, the implementation of extracting the freelancer's hourly rate is a simple case freelancer, string name double hourly rate, or var name var hourly rate if you prefer. And if we want to add a condition, we use a so-called guarded pattern. After any pattern, we can write when and then some Boolean condition, and of course the branch is only executed if the condition is true. The astute among you may wonder how this interacts with exhaustiveness. Clearly a case freelancer when hourly rate larger than 250 does not cover all freelancers. Can you add a case freelancer when hourly rate is smaller than or equal to 250? Yes, absolutely. But it won't do what you hoped. The compile error would still be there. The reason is, well, that computer science is very mean. If you allow arbitrary checks after when, it is categorically impossible that the compiler can figure out for all conditions whether all possibilities are covered. You could limit the kind of conditions and then implement a checker for that, and then make all that part of the Java specification set in stone for eternity. Or you just don't. Treat any guarded pattern as inherently incomplete and require an unguarded pattern for each type to achieve exhaustiveness. So in this case, just add a case freelancer without any when after all the case freelancer when, and the compiler is happy. Yes, you don't get to express the symmetry of larger than versus smaller than or equal to, but unless you're like me, you're probably not going to lose sleep over that.
Hello, darkness, my old friend.
If you want to learn more about data-oriented programming, watch Inside Java Newscast number 29 or read Brian's seminal article on the topic, both linked in the description. For now, I want to leave you with the 4 principles he defined. First, model the data, the whole data, and nothing but the data. That's the part about creating types that match the shape and alternatives of the data closely, as well as the part where you do not add operations as methods to the data, but as functions operating on them. Second, data is immutable. That were the records and the immutable copies in the constructor. Third, validate at the boundary. And fourth, make illegal states unrepresentable, both of which are covered by designing types correctly and rejecting illegal combinations of data in the constructor. And that's it for data-oriented programming. Right. Phew. That was close. You don't want to know what happens to YouTubers who foreshadow something and then don't follow up on it. Whew. I let you hanging on how to combine multiple types into one branch with defaulty behavior.
Hello, my name is Angelos Biboudis and I work for the Java Platform Group at Oracle. There are numerous cases where we want to describe some functionality in code while clearly expressing that some elements can be ignored. Java 21 reintroduces the underscore character as a preview feature to be used for ignoring pattern variables, whole patterns, or other kinds of variables outside pattern matching. Let's continue the employee management example and add an intern record. Imagine that we would like to write code that processes the first case but does not care about the other cases, as our abstract data type is today. We can express this with default. That would indeed make the switch exhaustive, however there is a hidden caveat. While this switch is now exhaustive, it is not future-proof. If someone adds a new variant in the future, the snippet will never fail to compile or execute. The compiler can do a better job of checking exhaustiveness without a default case. If we want this switch to signal us back a missing case upon recompilation, there is indeed a better option. We include the variants of freelancer and intern. Notice that both f and I in this case are now unused pattern variables in our code. We can replace both with underscore and make our intention that we do not care about variable names clearer. Since those last two cases do not introduce any variables in the scope on the right-hand side of the cases, we can remove the duplication and write this more succinctly in one line. A case with multiple patterns that none of them introduces pattern variables. This version of the switch is decluttered and offers error reporting upon extension of the data type. Unnamed pattern variables can be used in nested positions as well. For example, when we deconstruct a salaried employee in this example. But also for whole nested patterns. Here underscore in the first case is an unnamed pattern. There are other valid cases of unnamed variables, for example in try with resources, when the resource name is not needed.
Thanks Angelos. He's the owner of JDK Enhanced Proposal 443, which introduced unnamed patterns and variables as a preview feature in JDK 21. I'll tell you more about that in our Road to Java 25 video series in 2 years. Because we're done, not only with pattern matching and data-oriented programming, but with the Road to Java 21. From upgrade hurdles to virtual threads, from better tools and security to improve performance in APIs, and now pattern matching, we've covered everything new between Java 17 and 21. We really enjoyed creating this series and everybody invested a lot of time and energy to make the best videos we could. If you like them and have the chance, leave a few nice words for Anna, Billy and Jose in the comments here or under their videos. I'm sure they'll love to read them. Another person who deserves praise is David Delabassi, who created the intro, the thumbnails, and is generally the good spirit behind our YouTube channel. Thank you, David. All that said, I hope to see you again in the next weeks and months for regular programming, Jab Cafes, Stack Walkers, Inside Java newscasts and podcasts, conference talks and more. This is the best place on YouTube to learn deeply about Java. Subscribe and I'll see you around. So long!